And well, now we start with the plenary talks. The first one will be delivered by Johan Weber from the National Renewable Energy Laboratory. So thank you. Let's see.
Yeah, this one.
Is it correct?
Yep. Just put it on display. So, hello everybody. You might be surprised to see me here because Paul Weers, my colleague, was supposed to come. He unfortunately is not seriously but temporarily sick, so he couldn't come. So I'm trying to, I have the honor to try and step in for him. A few words about Paul. Paul has over 45 years experience in conventional wind turbine research. He was the leading researcher at Sandia National Labs for about 30 years. He came as chief engineer to the National Wind Technology at NREL about 10 years ago. And he's now moved on as the chief engineer to a senior research fellow, which are very prestigious positions, kind of wise people at the end of their career in the lab. We're about 4,000 people, there are only about 10 fellows. And yeah, so lots of questions that might be coming up. Please follow up with Paul afterwards. And since we're stepping in here to fill the gap, also Roland is helping out, and he's taking what we have here from conventional wind and reflecting on it and how it might turn out for airborne wind. Okay. All right, so the presentation is about the grand challenges in wind energy research and the needs in order to achieve what the overall aims are. 4 different generations, not necessarily generations of technology, but generations and eras of research have been identified. So the first one, we have the wind and the rotor itself, turn flow into torque. Next one is the turbine as a system. Then we move on to the plant, interaction with the grid, and later on, future energy system. On the right-hand side, with the mindset, you see the ambitions that these different eras or generations have in terms of desired contribution to the total energy provision in terms of electricity. So generation 1 was about get it to work, but now in generation 4, we really want to drive the energy system. Let's look at these first generations. So as mentioned, the first one is the rotor. So it was all about aerodynamics, about flow conversion, energy conversion, and additional some early standards and some early codes. Make it work, make it survive was basically the essence of it. However, as you see on the right, this simulation is not from that era, which also means the point that we're coming back to later on, that we still, at these generation 1 issues, still need to work on them, still need to improve our tools and progress on them, as everything that comes after builds on it. Generation 2, the turbine. Now we have a multidisciplinary, multi-subsystem, highly interactive system. So we have wind models, we have structural models, we have aerodynamics, we have hydrodynamics as we go into the water, we have multi-body dynamics and power electronics and control and servo motors. So here, this generation had the goal to optimize the interacting system as a whole and bring the costs down so that things become not just commercial being a product, but also economical. Next step is the plant. Now with the plant, it's important to think of plant control. Here the spinning brain at the bottom indicates that plant control. The most obvious effect, of course, is wake steering, but also the control of the plant on the power side and all other interactions, communication, and there might be also additional instrumentation like LiDAR within the farm. And 4th generation is the energy system. Here you see a very nice simulation of the North American energy system. This is not exactly the US, there's Canada in there, and it's also split not by jurisdiction, but by domain, and on the left-hand side you see states. And you're running through one day. You can see the time clocking here. You also see the shadow of the night coming over here, or the lack of the sun, not the shadow. So this slide is about saying, hey, when we're going up to 30 or 50% off the grid, we have very different issues. And we do not just need to comply with the requirements of the grid as an energy provider and stabilize it. We actually have to run the grid. So a very different set of demands and tools required. So if we can now go back and reflect on this pyramid, we really see the ambition on the right and the contribution that we earlier showed. I think there's a bit more merit behind it now to understand what these generations mean. Back to the point that we still have to work on the earlier generations as well. So in Paul told me in 1981 at a conference, the understanding was, okay, we understand the blades now, we understand, we have blade element theory and we have a few fudge factors, so we understand these things. And there was a reality check in 2000 where different codes were tested against empirical data of a device or of a turbine that was not conventional at the time, not 3 blades, no twist in the blades, very kind of unconventional, and that turned out that the simulations were very much off from the results, which showed that the tools at the time were not physically bottom-up predictive. They were basically customized to fit the typical design, and then you could vary around with it. So there was another important insight to see that a huge increase in fidelity and physical accuracy has to be done when you want to optimize systems out of the customized domain. So just to say that we still need to work on generation 1 and generation 2. And that holds for the whole pyramid. So we really have big gaps. So the depth and the scope has increased, but the funding has not. So there's a lot of gaps to fully implement this vision, to have the generation 4 driving the energy system, and now on top of it with carbon-free operations to build that up. So we need these to come in. And these are a few themes that I envisaged to underpin this here, to achieve the grand challenges. And we can go into these a little bit further. But first of all, really to realize that the grand challenges, they expand from the global weather system right down to the minutiae of the material science, of subsystems, of subsystems, components, all sorts of flows in between, information, forces, energy, everything. So it's hugely complex. And to realize the carbon-free energy system, we have identified different themes. So the physics in the atmospheric flow, the system dynamics, but also the grid and the optimization of all of it together. Digitalization is a hugely important aspect, and also because we're thinking about new problems, education, and the overall system perspective. We now have a quick run through what kind of themes and topics are required to be dealt with in order to achieve this 50% supply to the global electricity. There are relatively recent, within the last 2 years, publications about all of these 10 themes, and overview papers, also very recent from Paul, and I'm sure he's involved in many or all of them. And let's just go slide by slide through each of them. So atmosphere, turbulence situation. So we have multi-scale turbulence problems. And you see a diagram where you have logarithmic rough orders of magnitude in time and in scale and in energy content in these turbulent situations. And particularly the middle ground is not very well understood. So there's a lot that needs to be done here. Then we go on to atmosphere, mesoscale, wake. Now this is not the wake of the wind turbine within the field, it's the wake of the plant itself. So it's a bit like the inverse. Instead of looking at complex terrain and what the inflow conditions to the farm is, which we've been trying to do for a long time, this is now looking what the consequences of the flow through the wind turbine, through the plant is onto the environment. And you see a complex terrain here, and the moving parts are the flow fields and the wake of the plant. And in the next one, we have the offshore situation. Of course, there's quite a few, and maybe more than one would think immediately, things different. First of all, of course, we are in a situation where marinization of the system is required. You might have to have air conditioning system on the machine and things like that. But also the flow fields are quite different. The flow is different. There can be more shear. We have a microclimate on the coast. The direction of wind directions can be much more variable. So there's a lot of things to be considered in this situation. And when we move to the turbine and look at developments in terms of turbine sizes are larger, turbine hub heights are higher. It turns out that now that the codes that were written for the lower layers are not actually valid anymore, so the load conditions are different. At the same time, the system is more optimized, so this optimization goes deeper into the system. It goes for, in terms of control and power and response, right into the generator and the power electronics. Of course, we're larger, so we need aeroelastics and everything that comes with it, and material science. So the interaction and the system perspective is becoming more and more important, and several other problems I haven't mentioned here. On farm, we've mentioned this before, farm control, probably using new instrumentation, not just the instrumentation that we would have on the turbines themselves. What comes with it is also that plants may not be homogeneous. They might have different combinations of turbines. And of course, we need to look at algorithms, and in validation, we have very little data for these situations to tune those models. Grid, and again here, hugely interactive. So you see the grid at the bottom, then you see plants, maybe hybrid plants, or you even could have to consider fleets of plants that power the grid. And that goes into the control of a plant itself and into the machine, and even into alterations in the machine, like having storage on board of the machine. That was done. It hasn't taken off, but it was at least considered. And then digitalization, of course, there is a lot of data around within the individual machines. Unfortunately, it's not standardized, it's not accessible. So there's a lot of knowledge that is not being tapped into, and you'll get a great insight from Sarah later on this topic. And co-design of environmental aspects. I like the word co-design finally applied to the environment, with the hope that we maybe can improve even something. What's the critical aspect here is that if we move on to a penetration of 30 to 50% of renewables, so of wind, the currently possibly acceptable interventions into nature with bats being struck by wind turbines will not be acceptable anymore, because the bats population doesn't increase with our penetration of the grid. So there has to be a much harsher implementation of environmental compliance, and things need to be taken into account, for example, in particular terrains where eagles take the updrafts, so make sure that these are not being interfered with. Social acceptance, of course, hugely important when we've come to higher penetration. On the right-hand side, you see 3 estimations for total capacity in the US, and the only difference between them is the setback from the turbines to turbine, and from turbine to the next infrastructure, like houses and things you need to stay away from, also associated with height, flicker, noise, and multiples of rotor diameter. So depending on how harsh these requirements are, you can drop down to 15% of what you could ideally get with short setbacks. And small wind turbines have been kind of neglected in the research that's been done for them. Of course, there's less capital behind it, but they need their own tool development, their own technology development. They work in different conditions, they have different clients, they have different requirements of lifetime, there are different O&M situations, so they're basically a different technology that needs its own technology development roadmap, its own tools. And that absolutely is, of course, totally the case for airborne wind. And maybe there I leave it, and I just want to plug in that we have the next NAWIA conference coming up in the US. The abstracts are due on May 17th. I want to thank the 4 or 5 speakers that came over last year. So we were able to put an airborne wind session into the conference for the first time. Thank you very much. And hopefully we can make 2 sessions filled this time. And that's it from me, and I'll hand it over to Roland.
Next?
No, desktop. Go to desktop. There is a PowerPoint of this one.
Okay.
Yes, so I think, thank you, Joachim. This was a great, let's say, outlook for us, because we are not there with airborne wind. Of course, what you saw here has 40 years of development, at least, spanning, while we have something like 15 years, maybe 20 at best. So there is a lot for us to catch up, but there are a lot of similarities between wind and airborne wind. And I think we can make use of the approach that wind has taken. Although, of course, now wind is there, and we really have to deal with that. How do we bring now airborne wind into the picture? I have made here a slide in which I want to point out. Until now, we mostly worked on the centerpiece, the airborne wind energy technology development. This is where most of the effort went into. We have spent a lot of effort on control. Control is probably even the discipline that kicked off airborne wind as for technology development. We have spent a lot on optimizing flight trajectories. There is great research out there, but this is of course not enough to make this a profitable commercial technology. That's what we need to go to. And I put here the 5, maybe there are more, sectors around the actual technology development that we need to deploy the technology. And on the left-hand side, what I mean with business development, this is basically what happens at companies, right? That's what you need to do to make a profitable business. You need to look at the markets, resource assessment, how to upscale the technology, supply chain, public funding. You need to have money to do these things, and private funding. So that's one of the sectors. Then if we go down to regulation and certification, that probably picked up only like 5-6 years ago, slowly. We came from individual permits at, let's say, where we tested our prototypes, but now we see more and more that we need an approach how to do that as a discipline to actually have many kites flying, and that's a whole different ball game, going from the prototype testing to a deployed technology. And I list here all the different things you need to look at. And we heard great news yesterday about, for example, standardization, certification. We heard a debate, and it's not clear yet where we are going. Then if we move on to environmental impact, that's also something that's only happening since recently. All the prototype installations, they need, let's say, to analyze their impact, but then what does it mean on the level of technology deployment? That's still something that needs to be found out. And then social acceptance, it's another big field. We have the emissions of the systems, the acoustic emissions of the systems. Then the psychoacoustics mean how do they act actually on people and animals, and maybe also plants. So that's something that I think is just in the baby shoes right now. We have a research group, just kicked it off in Delft, with the purpose to look at psychoacoustics. Now that we have noise, finally we can also quantify and analyze the impact of this on people. We start with people. Then this last sector here on the right top, research and education, that's of course my core business, where we provide support to the companies on the left who actually built the prototypes. And what happened so far is that I would say we individually worked on our fields where we are good at, but what's missing still is this networking, the joint collaborative approach. We have the IEA Wind task in here. If you click now through, there should be little thingies popping up. For example, of course, IEA Wind task 48 on airborne wind energy is very active in this centerpiece. Yesterday, work packages 1 and 2 together, I would say we had a full room, maybe over full. You see there is strong interest and also many collaborative things happening. We have software tool chains that are open and that can be used by others, and it was great for me to see that people are already using these tool chains and reproducing our results. The first step for validation, I would say, because if others look at what you're doing, it's a key principle in science, then you have an opportunity to improve that. If you click further, And now you can just click through. You see we are also active with the IEA Wind task. No, back. In the other tasks here, maybe even in some of the aspects here, resource assessment in the business development part. So it just started, and I think we have everything set up to maybe look at our grand challenges, as you formulated it, Joachim. But we still need to solve, I would say, many issues, and that's also the fun of it, especially for us researchers, but I'm sure also for the commercial players to work on these challenges. There is a lot of similarity with UAV technology and wind, and we try to bring the two sectors together. That's all I want to actually say about this. Thank you.
Maybe we have time for one question from the room to Johan or Roland. Someone? It's clear we are at the beginning of the conference and the attendees are shy.
Yeah, for example, it's a good question, thank you. There is, of course, I would say from own experience, we see if we fly kite power systems or airborne wind energy systems, we penetrate into the same airspace as drones. And that was always a bit a problem if you have to share airspace. We have a tether, and that's not something that untethered drones really like. But I also see that there is a lot of technology that we can actually integrate into airborne wind. And I hope that there is also some technology that can go the other way around. Of course, UAV sector is a lot bigger than airborne wind, so it's probably not a balanced view. This is basically what I meant.
Okay, let us thank the speakers.